Hey everybody, so today I want us to actually tackle like a workout problem, right? And in my school, with our workout problems, we have to take like a certain type of format, right? So basically, I have a problem that says water is contained in an insulated free piston cylinder device and has a mass of 0.3 kilograms. Initially, water is at 100 degrees Celsius and 500 kilopascals. Some amount of heat is added until the temperature is now 200 degrees Celsius. Find the following. A, the total initial volume, which is V1. B, the work done. C, and the total heat that was transferred, right? Now in my school, they want you to do things like find the system, the sketches, including a state diagram, which is like a PV or a TV diagram, conditions, physical laws, properties, and calculations, right? Now, first of all, what I like to do, this is how I solve these problems. I first find a system, right? So my system, they literally give it to you. It's low-key 3 points. So a system would be a free piston cylinder. Well, it's an insulated free piston cylinder. You want to give them as much detail as possible so that they don't have any space to dock you on points. So I wrote an insulated free piston cylinder with water, right? You can write containing water and so on. And then what I like to do, I know I said you should give sketches, but I like to find my properties first. So they gave me mass, right? Let me write this here. They gave me mass as 0.3 kilograms. And then they gave me temperature. Initially, water is at 100 degrees Celsius and 500 kilopascals. So my T1 is 100 degrees Celsius and my P1 is 500 kilopascals, right? And then it says some amount of heat is added until the temperature is now 200 degrees Celsius. So that means that my T2 is 200 degrees Celsius. And what I like to do, and my mass generally stays constant, so my mass is still 0.3 kilograms. And what I like to do is then go on to find my properties at that point in time. So we're dealing with water here, right? So what do we have to use for water? We have the tables, right? So first what I would go and do here, right, is find what state that is in. And I already know that this is in a compressed liquid state, right? I'm just gonna write CL, right? Compressed liquid. And what we do, I haven't gotten to the point, I think at a point in time they start using something called compressed liquid tables. But what we do in Thermo 1 is we take this as though it's a saturated liquid, right? So all of the values here, I'm gonna find as if I were finding for a saturated liquid. So I would find the values for a saturated liquid at 500 kilopascals, right? Or at 100 degrees Celsius. And I found that V1, my specific volume, is equal to 0.001043. And, oh, maybe I should move these over a little bit. But this is just meters cubed. You know what, I am going to move these over. My T2 is 200 degrees Celsius. And this is meters cubed per kg, right? And then, what can I find now that I have my small V1? I can find my big V1, right? Now my big V1 is equal to this 0.3 times this, right? Because my mass is equal to, my volume is equal to mass times specific volume. So when I multiply these out, I get times 0.3, I get 0.0003129. And then this is in meters cubed, right? And now what we can do, I've gone ahead and I've used an equation, right? So they want the physical laws that we used. And I went ahead, so this is sort of where you can like list your equations and everything. We can go ahead and write that. I'll write that over here. And then I'll erase these when we're done, and then we can look at the diagram. Because this is basically like I was doing this practice problem and I didn't do some things right, so I have to just double check myself and make sure that I'm doing them right. But I can just basically say that like big V is equal to small v times m. So that's my mass times my specific volume. So what else can I find? I know that it's asking me for total initial volume, right? So I've already gone ahead and I found the total initial volume. Simple. So we've gotten, so A is already done, right? So I know that that is correct. And they're not asking us for the work done. Now, what do we know about a free piston cylinder? In a free piston cylinder, pressure is constant, right? So I know that my P2 is equal to my P1. So I can go ahead and write that P2 is also equal to 500 kilopascals. So P2 equals 500 kPa. And I love to fill up these tables because I feel like it shows the grader that I know what I'm doing, right? So because that is 500 kilopascals, how do I now find the work done? Remember I talked about something called boundary work. And I talked about boundary work is basically the integral of I'm writing this here because we're going to use this equation. But this is just the integral of V1, and they're asking for big V, big W rather. So the big boundary work done, not specific boundary work, right? So this is our volume 1 times our volume 2. And the reason I write this, maybe for those of you new viewers, I write this volume like this to show that it's volume and not specific volume, right? So this is the integral of V1 times V2 of P dV. And what can we do with an integral when we have a constant? We can pull that constant out and we get this, P delta V. So our boundary work is going to be equal to P delta V. But we have to find out what our delta V is first, right? And that delta V is just V2 minus V1. But what are we missing in terms of V2 and V1? We're missing V2, right? We have our V1. So V2 is going to be equal to, we're going to find the volume at this point in time. So we have to find out if it is, what state it's in. So I'm going to go ahead and grab, I don't remember offhand what state it was in. So I'm going to go ahead and look at my tables, right? I have my book here, and then I'm going to find what state it's in. So it's at 200 degrees Celsius and 500 kilopascals. So I'm going to go ahead and go to the pressure table, look at 500, and I can see that it's above the saturation temperature, meaning that it's superheated, right? So I'm going to go ahead and go to my superheated water tables. Because P is greater than Psat, it means that it's a superheated vapor, right? It's already gone past saturation point. It's already boiled and now it's a complete vapor. So I'm going to go ahead and go to my tables, and then I'm going to go to my at 500 kilopascals and at 200 degrees Celsius. That's where I'm going to get my values. So 500 kilopascals is equal to, I believe that is equal to 0.5 megapascals rather. Yes. So at 200 degrees Celsius, we have that our V is equal to 0.4, our specific volume is equal to 0.42503. And that means that we can find our big V2 now, right? And this is just because this mass stays constant, right? So we know that our mass at our state 2 is still 0.3 kilograms. And when we can multiply this out, we can find that our big volume is equal to 0.127509. And this is meters cubed per kilograms. And this is simply meters cubed because we get rid of that kilograms by multiplying through by mass. Now, what we can find, we have all of the tools, right, that we need, right? So we can go ahead and multiply this out. This pressure stays constant. So this is this 500 kPa, right, times our delta V, which is 0.127509 minus 0.0001 3129. And when we do this, we get, and you should be doing this on your calculator also, just to make sure I'm not making any mistakes. We get that our boundary work should be 63.598. Right? And that is in kilojoules, I believe, because it's not specific boundary work. So they're asking for big boundary work. So it's simply just kilojoules because work is given in kilojoules, right? That's our SI standard unit. They also ask for, so we've done this now. I know that is right, or hopefully it is. Now they're asking for the total heat that was transferred, right? Now, I don't think I've talked about this, but we have a closed energy equation. And I probably should have talked about this when I was tackling closed energies. But we have something that says that the Q in minus the work out is equal to the change in energy, right? Q minus W is equal to delta U. And this work in this situation, I believe it's going to be boundary work, right? So for this specific equation, for our physical law, we have Q minus W equals delta U. And for me, the confusing thing is sort of just, this is sort of net heat minus net work is equal to delta U, right? And here it's just going to be Q in minus Q out minus W out minus W in. And that's just sort of confusing for me, but you just want to know that, basically it's just what I just said, Q in minus Q out minus W out minus W in. But what we have here, we're sort of missing something, right? And I probably should have left a little bit of space for this. But we're missing our U, right? Now we have to go back to our tables, right? And since we know what state this is in and know what state this is in, it's going to be pretty simple to find. Now we're going to find, using my tables, I go to my tables and I find that at 100 degrees Celsius, UF is going to be 419.06, and that's kilojoules per kilogram, right? That's my specific internal energy for, what number did I say? 419.06 kilojoules per kilogram. And in U2, I have to go to the superheated tables, right? When I go to the superheated tables, I find that my U is going to be equal to, give me a second, guys. So I go to 0.5 megapascals because these tables are generally given in megapascals, but I know that that's equal to 500 kilopascals, sorry. At 200 degrees Celsius, my specific internal energy is 2643.3. And that's kilojoules per kilogram, right? And I'm just writing this up here because I have a little bit of space. I would normally write this like down here. But now we can find our big U's at this point in time because we know our mass and we know our specific U's. And what I can go ahead and write here, they're not really too concerned about all of the formulas that you're using. They are, but not. I've basically made it clear that I know that multiplying mass times a specific quantity gives me my quantity big, right? So my volume is equal to mass times specific volume. But I can go ahead and write that my big U is equal to mass times little u, right? Okay, so now when I multiply these out, I get that my big energy is equal to 419.06 times 0.3, 125.718. And that should be kilojoules. Kilojoules, right? And my U2 would be 2,643.3 times that 0.3. And that's going to be 722.99 kilojoules. Now, I have all of the tools that I need to find my, they're asking for Q, so the heat transferred, right? So that Q is going to be equal to, once I rearrange the equation, that Q is going to be equal to boundary work plus my delta U, right? That should give me my Q, and when I do that, I've already calculated my boundary work, so this is building on itself. So I get that that's 63.598 plus my delta U is gonna be, that's gonna just simply be U2 minus U1. So that's my 722.99 minus my 125.718. And that should give me my final answer. Now let me calculate that out real quick and see what we get. 63.598 plus 722.99 minus 125.718. And that gives me 660.87. Or no, I'm sorry. That does not look right. Let me see. That's not the answer I got. And this just shows that you should really double check your work and everything. Okay, maybe I got it wrong. But basically, the final answer I get is 660.87. And that's going to be given in kilojoules. And that should be your final answer. And you can go ahead and double check me on that, because I wrote something down different on my paper. But now that I'm doing the calculations in person, I see that I get a different result. And I just double checked myself, and I believe that should be the answer. And yeah, that makes a little bit of sense. So again, if you have any questions, oh no, we're not done again. We're not done. We also have physical laws, but we also have something called conditions and our sketches, right? So we also have the sketch that's going on. Basically, what we've used, these are all the formulas that we've used. So I think we're good on this. So I'm gonna go ahead and erase all of this. I hope you understand what I've done up to this point in time, right? But I also have state diagrams that I need to draw. So because we're dealing with a phase changing object, our state diagram is gonna look a certain way. When I was practicing this, I didn't draw it properly. But basically our state diagram is going to look like, we're gonna go ahead and draw a PV diagram, because we've not learned about S, which is entropy. We have learned about T, which is temperature, but not S. So basically, we're gonna have a little graph, right? PV. And what we're gonna end up doing, we know we have our dome. We know that, right? Where this is compressed liquid, a mixture, and a superheated vapor. And we know that we have our constant pressure line, right? And this is obviously going to be our 500 kilopascals, because from P1 to P2, we didn't really change our pressure. Now, because we have a V, right, and a P, what happened as we were increasing in, we added heat in, right? So that piston started expanding, right? And the total volume increased, right? So we went up, and we sort of we saw that it went from a saturated liquid, so this is going to be my point 1, right? So I'm going to label 1 right there. And it went to a superheated vapor, right? Now, we don't exactly know what specific region this is on this graph, right? But we know that it's going to be somewhere on this area. So generally, they know that you don't know the specific area, because this isn't really to scale, right? But I know that it goes from state 1 to state 2, right? And I'm just going to put a little arrow there, right? And that sort of just basically shows everything that has gone on, right? For phase changing substances, you're gonna want the dome PV graph, right? For if it were like air, right, it might have done something like this. Let's say we were dealing with air, and the pressure. Let's say the pressure went up and the volume went down. So we would deal with we would end up with something that looks like this. Pressure went up and volume went down. So we would deal with something that looks like this. You get what I'm saying? So you just have to like sort of, that's why I always do these at the end, because it's pretty simple to just figure out what has gone on, and I would label this like 1 and 2 if this were air, right? But this is H2O, which is a phase changing subject, a phase changing system, or substance rather, and that's why I drew this graph. But basically that's what your PV diagram should look like, because state 1, it was a saturated liquid. That's why it's just on the edge of the dome, and it went past all of this and turned into a superheated vapor, which is why I use my superheated tables, and then that's where state 2 ended up at. So that's your PV diagram for the phase changing substance. And then I also talked about something called conditions. Now conditions are just basically, let's see how well the black is working. Let's go ahead and use that orange. Conditions are basically just like everything, just describe the system. So conditions, I would write, you can write like phase changing substance, I guess. And what I've come to notice, like, if you give more, granted this is a fact, so they might not look at this as a condition, but they're not going to dock you points for it, right? Another thing, what we're dealing with like a constant pressure process, and to sound really smart, instead of just saying like constant pressure, just write isobaric, or isobaric. Some people pronounce it isobaric, right? What else were we dealing with? We dealt with, let me see. We dealt with, you could say no kinetic energy or potential energy, because it's a static system, right? No KE or PE involved, or change involved, I would say, just to be more specific. What else? Okay, there was heat transferred, there was work done, but do we have mass transfer? No. So you can write like no mass transfer. And basically, or you should write isobaric process. And basically, whatever you can think of, I suggest just write it on. Get as many points as you can. But basically, this is the type of problem that you are going to encounter in thermodynamics. And this sort of builds up on itself when we get to dealing with things like diesel engines and patrol engines, right? I mean, these are just tools that help us know sort of what's going on in the system, right? And I mean, I hope you guys have understood what I have done here, because I mean, it's not too tough, right? This was a pretty simple problem once you break it down and look at it. But if you're a little bit confused and need a little bit of help, just go ahead and leave questions in the comment section. Whatever question you have, I'll do my best to answer it. And please tell your friends, and don't forget to like and subscribe. Please make suggestions on what type of videos you want to see. Remember that I'm still taking Thermo 1, so I'm learning just like you guys, but I'm doing my best to explain what exactly is going on here. So please let me know what topics that maybe I don't cover that you guys would like to see, or you feel that I'm skipping over, and let's get to it. Let's learn Thermo, y'all.